Exercise 3E and 3F, Determining Transformations and Sketching. Today we are learning about determining transformations applied to a function and then sketching this transform function. What you need to be able to do is rearrange the equation in terms of old x and y, determine each transformation applied to old x and y, and then sketch the transformed function given these transformations. So what are the rules for determining transformations? It's going to be actually a lot easier to be able to work this out or understand it while we're doing the examples. But just to give you a bit of a guide, I've tried to separate them out into 4 steps, which are really just the reverse of what we've been doing previously, where we're applying transformations. So this time the transformation has been applied and we're just trying to figure out what those transformations are. So in general, what we want to be able to do is to isolate x dash and y dash, so that's our new x and new y, in terms of the old x and y, to understand the story of what happened to x and y. So we want to see what's been multiplied or added, what's happened to x and y to cause it to become the new x and y values. So here are the 4 steps. First of all, you want to rearrange the equation to get x and y on separate sides. So everything that is pertaining to y, get it on one side, and everything that is pertaining to x, get it onto the other side. Then we want to equate the transformed equation to the original equation. So equate the y's together, the x together. Then rearrange to get the equations in terms of y dash and x dash so that we can understand what happened to x and y. And that's going to help us to read the transformations. So as I said, I think this will make a lot more sense as we go through it as an example. So example 7. Find a sequence of transformations which take the graph of y equals x dash to the graph of square root of x to the graph of y equals square root of 2x minus 1. First thing that I like to do with these is the new or transformed function. I like to put little dashes there just to make it very clear to myself that that is the new or transformed function. In this case, that first step where we need to rearrange to get y and x on separate sides is actually already the case. So if I were to write the 2 equation, I've got y equals root x, that's already separated, the y's and the root x. And then if we try it with our new equation as well, that's y dash equals root 2x minus 1. There's nothing that I can move over to this side. So if I had a plus something or multiplied or negative or whatever, that's what I would move over. But in this case, it's very clear that they're separate. So that's step 1. It's already done for us. We didn't really have to do much. Step 2, we're then going to equate the 2 sides together. So you can see this is the y side and this is the x side. So just like we did in our previous examples, we would say y equals y dash, and in this case, don't take what the actual function is, but rather just what's happening to x. So that would be x equals 2x dash minus 1. So if you recognize, we're at that point now where old x and old y are by themselves, where usually we would go ahead and substitute it into the original equation to get the new equation. So now we're at a stage where we want to get x dash and y dash by itself, so that we can see what has happened to the old x and y. So we'll go step 3. I'm going to rearrange the equations to get x dash and y dash by themselves. Of course, in this case, y dash is already on its own. So what that tells me is that there's been no transformations that's been applied to y. In terms of x, we're going to add the 1, and then we're going to divide by 2. And order does really matter. So whether I write this as x on 2 plus a half, that's going to give me a different transformation, or different order of transformations rather, than x plus 1 divided by 2. So here I can see that what's happened to x is first I've added 1, then I've divided by 2. So it doesn't really matter what order you actually go in, but what does matter is that it's almost like your BODMAS. So whatever is attached to x is what you need to describe first. Okay, so I've gone ahead and written 1 and 2 because those are the 2 separate transformations that I can see. And then step 4 is to go ahead and describe each of those transformations. So the first thing is that I can see that we've got a translation. So translate 1 unit to the right. And then we've got dilate by a factor of 1 on 2 from the y-axis. So remember, because it's attached to x, it's going to be from the y-axis. Just to make it clear why that's 1 on 2, because this is a fraction. This is like x plus 1 multiplied by 1 on 2. So there's our dilation there. So there we go. That's our 2 transformations, and that's the basic steps of how we do it. So let's practice it now with the next example. Okay, B, find a sequence of transformations which takes this graph to the graph of y equals 1 on x squared. Now you can see that this looks like the transformed graph, but in this case, because it's saying takes this to this, in fact, this is the transformed function here. So I'll just put little dashes just to make that very clear, and this is our original. So step 1, we're going to go ahead and isolate the y's on one side and the x's on the other. So with this one, what I can see is that there are two elements that are outside of the x function. I can take the 6 over and I can also take the 3. What's attached or sort of bounded by that bracket is what we can't move because that's specifically bounded to our x values. So when I take the 6 over, that's going to be minus 6, and then I'm going to divide by 3. Again, if you want to separate it so it's y on 3 and negative 6 on 3, you can do that. I'll just leave it over one fraction. Okay, so that's our original function, and then our new function, there's really not that much to write about that. So then step 2, what we're going to go and do is to equate the y's and equate the x's. So that'll be y minus 6 on y dash, not on y dash, on 3 equals to y dash. And then on this side, just as we did before, it's just on the inside that we're going to equate. So that's x minus 1 is equal to x dash. Now what you'll notice is that when we are going from a transformed function or one that has, different transformations applied to it to an original function, step 3, we actually don't need to do anything because it's already in terms of x dash and y dash. We already can see what the story is of old x and old y. So you just need to be careful. I know it feels a bit strange, but you are doing it correctly. There's nothing that you need to do in this particular step. So we can jump straight through to step 4, which is to determine what transformations have occurred. I'm going to go ahead and label them just so that I know which order to talk about. It doesn't matter whether you start with y or x, but as I said earlier, it does matter what transformations, the order of the transformation. So because the 6 is bound to the y, there's invisible brackets in a fraction, we're going to describe this one first. Then it's been divided, and then for the x, I'll just write that as third. So let's go ahead and work that out. 1, we're going to translate 6 units down, or if you want to write it in a more fancy way, you can say in the negative direction of the y-axis, which is probably the nicer way to write it, but this is just quick hand. We're then going to dilate by a factor of 1/3 from this time it's from the x-axis because it's attached to the y values. And finally, that -1, we're going to say translate 1 unit to the left. And there are your 3 transformations that have occurred in this equation. If you kind of think about it in terms of how do I get from here to here, if my function was already at +6, how do I get to my original? I would need to go down by 6 units, which is exactly what this is describing. All right, part C, find a sequence of transformations which takes this graph to the graph of y equals x squared. Again, we've got one of those graphs that have already been transformed and we're going back to the original. So we can expect that step 3 is not going to have anything to do with it. Or not, we don't have anything to do in step 3. All right, step 1, we're going to separate the y's and the x's. Here, I can see that this is bound in the bracket. Everything else goes over. So that'll be y minus 6 equals 5x minus 1 squared. And I did forget to do this. Put your dashes in, very important. That's y dash equals x dash all squared. Step 2, we're going to equate the two sides. Step 3, we're going to get x dash and y dash by itself, but that's already done. And step 4, we're going to determine. So I'm just going to label the transformations so that I know what to write. So that will be 1, 2, 3. Again, just follow BODMAS so that you know which order you need to describe. So number 1, we're going to translate 6 units down. 2, we're going to dilate by a factor of 5 from the y-axis. And 3, we're going to translate 1 unit to the left. Next question. The graph of y equals x squared is transformed so that its equation becomes that whole function there. Determine the transformations which have been applied. to y equals x squared. So this is our transform function. So the first thing is I'm going to chuck in the dashes and we're just going to follow the steps once again. So y equals x squared is all good. Here, the only thing that needs to remain are the ones that are inside the bracket, and I might just draw that in. That is all that needs to remain. Everything else needs to go to the other side. Everything else has to do with our y values. So that will be y dash plus 4, and then, so that's taking that one over, and then I'm just going to multiply everything by 2. Again, you can expand, and if you do expand, what that'll do is it'll change the way that your function, your transformations look. Okay, step 2, we're going to equate the sides. So y equals 2, y dash plus 4. And I don't know why I put a dash up there. That must have been confusing. Sorry about that. There's no dash on that one. That is our original function. I meant it to be squared. That's why. This squared is the function. So we only want the parts that are on this side. So that's x equals 2x dash plus 3. Step 3, we're going to get x dash and y dash by itself so we can see what has happened to x and y. So I'm going to take the 2 over by dividing it and then subtract 4 for the y's. And then for the x, I'm going to subtract 3 and then divide by 2. And then for step 4, I'm going to determine my transformations by labeling. So that'll be 1, 2, 3, 4. Okay, so step 1, we're going to go dilate by a factor of 1/2 from the x-axis. 2, translate 4 units down. 3, translate 3 units left. And 4, dilate by a factor of 1/2 from the y-axis. Hopefully you're getting the hang of it. It's just the same 4 steps over and over again. Example 9, state the transformations that have been applied to the first function in order to obtain the second. You might want to pause the video at this point and give this a go yourself, or you can follow along, but hopefully you've got the hang of it by now. It's the same thing over and over. We're going to apply the dashes. Step 1, isolate the x's and the y's. This is what is bound within the function. Everything else needs to go to the other side. So I'm going to subtract the 3, and then once the 3 is over, then I'm going to multiply both sides by negative to get that over. And then this is just as is. Step 2, I'm going to equate. I might just expand this. It doesn't really matter, but I'm just going to go ahead and expand that. And then only what's inside the bracket. Step 3, we're going to now rearrange to get x dash and y dash by itself. Again, notice when you go to a simple function where no transformations are applied, you don't need to do anything. So that's all good. We can tick that off. And step 4, we're going to determine. So as always, I'm just going to go ahead and label in the order of BODMAS. This one's a little bit interesting because there's a negative in front of the x, so you just have to pay attention to that. So the negative happens, and then the transformation there, and here. Okay, so 1, we've got a reflection in the x-axis. 2, translate 3 to 3 up. 3, then we've got a reflection in the y-axis. 4, we've then got a translate, that was written a bit funny, let's try that again. 5 units to the right. And then 5, we've got dilation. So dilate by factor 1/2 from the y-axis. So in terms of that for step 4, translate 5 units to the right. Why are we saying right? It's because in front of the 5, it's a plus. So this could be rewritten as negative x plus 5, and that can make it a little bit clearer in terms of what is what's actually happening there. All right, so that's the end of exercise 3E. We're now going to move on to sketching transformations, so that's for 3F. You've been sketching transform functions for a very long time now, but now it's just about being able to recognize what transformations have occurred. Now, if you don't know what they are just by looking at it, you now have this technique that we've just looked at to be able to determine the different transformations. But you should sort of get to a point where you can just look at it and figure it out yourself. So for example, if we have x minus 1 all squared, we know that this moves to the right. So even though it's a minus, it moves to the right because of the way that the transformation works. If we have 2x minus 1, that 2, remember, is a dilation by a factor of a half. So when it's attached to the x, when it's from the y-axis, it's the reciprocal, it's 1 on. So it's just those small things that you need to be able to recognize in order to sketch. So let's go ahead and apply it to a few examples. Sketch the graphs of y equals negative root x minus 2 minus 3. So there's a few transformations that have happened here. First of all, I can see that there is a reflection in the x-axis. And I can also see that we've moved to the right by 2 and we've moved down by 3. So that's for number 2. And I sort of just wrote them in one step, but that's number 2 and number 3. Other things that we need to note are the key features of this graph. So this is a square root function. With square root functions, we need to know what the endpoint is going to be. So the endpoint, it's kind of like your basic function is x minus h plus k, and your endpoint happens at h and k. So in this case, my endpoint is going to happen at 2 and negative 3. And we also need to find any potential intercepts that we might have. So let's find our y-intercept first. We can see that we can't take the square root of a negative, so there's not going to be any y-intercept. If we do have an x-intercept, we'll make y equals 0. So that'll be 0 equals negative x minus 2 minus 3. I'm just going to take the whole square root over to make that positive. So that'll be root x minus 2 is equal to negative 3. Now, even though algebraically this will work, right? All I have to do to get the square root over is to square both sides. In terms of it making logical sense, it won't really work because you can't take the square root of any number to give you negative 3. So even though when you try to do this, you will get an answer, it's actually not going to give you an accurate representation of what the x-intercept is. So at this stage, there is going to be no x-intercept because of this fact that you can't square root a number to get a negative number. And when we graph it, I think that'll make more sense as well. So let's go ahead and start graphing that on now. So it'll be our x and y. I'm going to put in our endpoint. So if I say that this is 2 and 3, so I'm going to go up by 2 every grid line. So that's 2 and negative 3. And as we know that there's a reflection in the x-axis, so our normal square root function does this, whereas our reflection would be looking more like this. And that's it. That's your transform function. Next example, sketch the graph of y equals this. So this is a truncus, and we can see that we've got a few different transformations. First of all, I can see I've got that 3 at the top. That is going to be a dilation of factor 3 from the x-axis. Those dilations, when you sketch it, don't really look that different, but what it will affect is the y-intercept. So it's always really good to show a point to be able to reflect that, and it's really good to be able to show the y-intercept to be very clear about that. We then have 2 translations, so I might just write it in one step as I did before. So translation of 2 units right and 4 units up. As we also did before we start sketching, we need to write about any special points that this function might have. Now this is a truncus, which means it has 2 asymptotes. Our x asymptote is going to be at 2 and our y asymptote is going to be at 4. We should also find any intercepts. So I'll start with my y-intercept, so I'll make x equal to 0. So that'll be negative 2 squared plus 4. That will mean that's 3/4 plus 4. 4 times 4 is 16, plus 3 is 19. So our y-intercept is 19 on 4. In regards to our x-intercept, we'll make y equal to 0. We might need a little bit more space for this, but we'll give it a go. I'm going to take the 4 over right away, just like this. I'm then going to go ahead and cross multiply. So it'll be x minus 2 squared is equal to 3 on negative 4. And then, of course, the next step is to go ahead and square root, but I can't take the square root of a negative number. So in this case, I have no x-intercepts. Okay, we can go ahead and start sketching now. So just to make it very clear, these are our asymptotes here. So I'm going to put them in. Again, I'll go 1 grid line is worth 2. And our x-intercept is 19 on 4, which is going to be 4.75. So if this was 2, 4, this would be 6. So it's just over it, just over here. And then we can go ahead and put our truncus in. I have totally missed the mark, so I'm going to give that one more go. Maybe with a thinner pen. Remember, our asymptotes are not allowed to touch, our function is not allowed to touch the asymptote. Third time lucky, I think. Not quite. See how this, I know I'm letting my my app just automatically make the curve, which is what's causing this. When you draw this, first of all, you should never touch the asymptote, and secondly, you should never veer away from the asymptote. So I'm going to give that one more go. I'm not going to let the app autocorrect. So we'll just let it do this and this. Whoops. Don't touch the asymptote. Now, in terms of the scale, we did say that 4.75 is around here, and my intercept has ended up all the way here. So you just want to be aware of these small things. It might be wise to put your intercept in and then purposefully make sure it touches. So I think that might be a more accurate sketch there. I'll label this. And make sure you also label all of your asymptotes. So that's x equals 2 and y equals 4. There you go, and that's your fully sketched function. That's the end of exercises 3E and 3F. These are the questions that you're required to do from your Cambridge textbook.